Okay, so now let's consider the effect of different compounding periods. So far, we've considered annual compounding, and what we mean by that is we've said our interest per year, and we've always used T in units of years. We need now to start being more flexible. So we're going to have to start thinking about compounding quarterly, daily, maybe even continuously. And we're also going to have to look at, when we get to bonds, things like annual compounding paid semi-annually. So the good news about making this transformation and generalizing what we've done is that everything we've seen so far in annual units can easily be generalized into really any compounding period that we want. And all we have to do to change from annual to quarterly or monthly or something else is just consistently change our time units. Okay, so if we wanted to go to a contract or a deal where we were interested in compounding quarterly, we would describe that as our percent interest compounded quarterly. And what that would mean is our percent interest would be paid every quarter, okay? So specifically, if we have $100 that we put into an investment paying 5% interest compounded quarterly, at the end of one quarter, we'd have $105, and then for the next quarter, that $105 would itself, all $105 would get 5% interest. So we would wind up at the end of two quarters with more than $110 through the magic of compounding. Okay, so when we do this, t equals 0 is still going to mean now, but now we'll say end of period 0 instead of end of year 0, okay, just so we can be more general. And t equal 1 instead of 1 year from now is always going to be one compounding period from now, okay. So if we're thinking about quarterly, we'd say EOP1 occurs 1 quarter from now. All right, so let's jump right into an example to see how to apply this. Let's consider, instead of a 3-year mortgage, let's consider a 3-quarter mortgage that could work like this. Let's say Mr. Big Shark Lenders offers Mr. Small Net Worth $30,000 to help him buy a $50,000 shack today. So Mr. Small Net Worth is going to buy this shack, put in $20,000 of his own money. If he goes through with this deal, borrow $30,000 from Big Shark Lenders, add to that, get a total of $50,000, give the seller the $50,000 and go from there. So to make this work, the contract that's being offered to Mr. Small Net Worth by Big Shark is that he would have to pay back 3 quarterly equal payments, okay, in a 10% interest framework, compounded quarterly. So this is the type of thing that we've done a lot on an annual basis, and we're just changing our time units and our compounding units to quarters instead of years. So we could ask the question now, how much is each quarterly payment? Okay, and it's still the truth, the whole truth, and nothing but the truth to say that the fundamental discounting equation still applies, and if we have a situation with annual payments, we can pull these future cash flows out of the summation because it's just one uniform cash flow, and everything we've done before still applies. We just have to remember that t equal 1 means 1 quarter, and R is our interest rate compounded quarterly. Okay, so in this case, we could expand to find PV tote, and which is equal to CF0, which in this case is going to be 30,000, is equal to that uniform cash flow that we're solving for, okay, times 1 over 1 plus our interest rate, 10% to the 1, where that's 1/4, plus 1 over 1 plus 10% squared, 2/4, plus 1 plus 10% cubed, meaning where cubed means 3/4, okay? So if we plug in CF0 equals 30, R equals 10%, we have the loan amount looks something like this, where we solve this equation for the cash flow, the uniform cash flow, and we find that after we solve that the uniform cash flow is $12,060. And this, you may note, is the exact same thing we found before working in annual units. And all we did here, all the algebraic formulas remain the same. We just carefully changed our units from annual to quarterly. We changed our interest rate compounding period from annual to quarterly. Okay. So the implications of this for Mr. Small Net Worth, I would argue, are pretty bad. So I'll leave the double A's in there to emphasize that. Why? Because now has to pay $60K every 3 months, not just every year. So remember, the first lender for Mr. Small Net Worth figured out that the maximum he could pay per year, sorry, it's not 60K, it's about 12K. The maximum he could pay per year was a little more than 12K, not every 3 months. So he's not going to be able to make those payments. And Big Shark Lenders is going to come along with someone who might break his legs, or worse, probably they'll take the keys to the house. He'll go bankrupt and he won't have a home. So that would be bad for Mr. Small Net Worth. Okay, so in general, in the real world, we're going to find that we're going to want to be comparing different deals or different investments, and some of them are going to be stated in quarterly compounding terms, some in monthly, some in annual, and so we need to be able to compare them on an apples-to-apples basis. And the way that we do that is with what's called the equivalent annual interest rate, or EAIR, okay? The equivalent annual interest rate is defined to be the amount of interest that's generated in a year in a certain contract or investment, irrespective of compounding period, okay? And we can always compute our equivalent annual interest rate, the amount of interest that this investment, this deal would generate for us in a year with this formula, okay? And the equivalent annual interest rate is 1 plus R, where R is in our native units, R compounded quarterly or whatever, raised to the number of compounding periods per year minus 1. Okay, so let's see how this works with a few real examples. If we have R is equal to 10% compounded annually, then the EAIR is going to be what? Just plugging in our formula. It's 1 plus 10% compounded annually raised to the how many compounding periods per year? 1. So raised to the 1 minus 1 equals 10%. So that's kind of a good thing. If we didn't get 10%, that something would be really wrong with our formula, because the equivalent annual interest rate for something compounding annually better be just that interest rate. Okay, so let's move on. So here's maybe a more interesting example now that we've checked the math a little bit. Let's say we're in a deal where the interest rate is 10%, but it's compounding quarterly. Okay, the equivalent annual interest rate is going to be what? It's going to be 1 plus 10%, but remember this is quarterly compounding. So how many compounding periods are there in a year? 4. So raised to the 4 minus 1 is 46%. Okay. So that's a lot, and that's the equivalent annual compound interest rate that Mr. Small Net Worth would be getting himself into if he took the Big Shark loan. So that's not so good, all right? But you can see the value of this concept, the equivalent annual interest rate, we can use anytime we want to make apples to apples comparisons with various projects of various compounding periods. All right, so it's going to be a really helpful thing for us. Okay, now one more thing about compounding periods that we have to consider is what's called the nominal annual percentage rate, known unfortunately as both nominal APR or simply APR. All right, and that's defined to be our native R times the number of compounding periods in a year. Okay, so our native R would be 10% compounded quarterly times 4 compounding periods a year. So let's put that in. For above example, let's see if we can type that in right. The APR is equal to 10% times 4 equals 40%. Okay, and the interesting thing about this, which I'll touch on more in a second, is that the APR does not tell us how much interest has accumulated in a deal over a year where we have quarterly compounding here. That would be 46% for the 10% quarterly compounding example. Okay, APR is something that is used often in consumer lending situations where they assume that people just can't raise anything to a power they can't exponentiate. So it gives a rough approximation of what's going on, but it does not give the correct answer. Okay, so we're going to try and steer clear of it. We'll use it a little bit just to make sure that everyone knows how to use it, but once we're sure that everyone understands it and knows how to use it, we're going to move away from it. Couple things to note. Nominal APR is universally agreed to, so whenever someone says nominal APR, they mean this formula, R times the number of compounding periods per year. Okay, unfortunately, APR means sometimes nominal APR, but other people use APR to mean equivalent annual interest rate. Okay, so what are we going to do? We're going to say throughout this text that our convention is whenever someone says APR, they mean nominal APR. Okay, so we will avoid confusion, at least internally here. Okay, so here are some examples of how and why we might need or want to use APR. Okay, if we have 7% compounded annually, then the APR of this deal is 7% times the number of compounding periods per one, or 7%. So we would say the nominal APR, nominal annual percentage rate of this project is 7% with annual compounding. Now let's go back to our quarterly example. We have an interest rate of 10%, but compounding quarterly here now. Then our APR, as I typed in above, is just 10% times 4, or 40%, okay? And we would describe this by saying the nominal APR of this deal is 40% with quarterly compounding, okay? And the APR itself is common in consumer world, but as I said, not very helpful because it's used in the consumer world more than we would like. We need to be able to turn it into something useful. So how do we do that? Well, if we just divide the APR by the number of compounding periods through the magic of algebra, that's going to get us R, right? So the nominal APR is equal to R times the number of compounding periods per year. So we could solve that for R. If we're given the nominal APR and the number of compounding periods per year, we could solve for R. Once we have R, then what do we want to do? Once we have R, we want to compute the annual equivalent interest rate. So we can always get to something useful from APR, but APR itself is not very useful, okay? All right, so let's do an example illustrating this. Let's say we have two money market offers that we are considering, okay? The first one, Bank 1, is offering 5% interest compounded annually. Bank 2 is offering a 4.5% APR with monthly compounding. All right, so let's start with what's easy. I'm lazy. I always start with what's easy. What's the equivalent annual interest rate of Bank 1? That is everything annual. It's going to be 5%. Starts at 5%. Everything's annual. Equivalent annual interest rate. The amount of interest we get in a year is going to be 5%. Okay. So what we need to do with Bank 2 is find its equivalent annual interest rate for its offer and compare it to that 5%. Unfortunately, we're given this stupid APR number, so we're going to have to solve for R from the APR, and then we can get the equivalent annual interest rate. Okay, so using that magic of algebra, solving the APR equation for R, we find that R is equal to the nominal APR divided by the number of compounding periods in a year. So it was stated as 4.5% monthly compounding, so that means 12 compounding periods in a year, or 0.375%, okay? Now we can easily get the equivalent annual interest rate, the amount of interest we will get if we put a blob of money in this money market at the beginning of the year and wait for a year. The interest we find that we will have earned on that at the end of the year is 1 plus our native R, 0.375%, raised to the number of compounding periods per year, minus 1, or 4.59%. Okay, so which one is better? Bank 1 offers us an equivalent annual interest rate of 5%. Bank 2 is giving us 4.6%. So clearly, Bank One offers us the better deal. Okay, so this example, again, purpose of this example was to see how EAIR is good for comparing different deals with different compounding periods, and also to figure out when you're given not the information that you want, but you're given the APR of a deal, how to convert APR to R, compounded monthly in this case, and then once we have the R compounded monthly, compute the equivalent annual interest rate. All right, so that's something we should all know how to do, because APR, like I said, APR, nominal APR, comes up in consumer lending a lot. Okay, so continuous compounding is something that was very popular in the 70s and 80s with banks. I think it's because they wanted to be really obfuscational and no consumer could figure out exactly what was going on. But it's still important for those of us who want to do anything with calculus in finance. So let's go over just the basics of it. So the idea of continuous compounding is that our compounding period is going to shrink to zero, and therefore the number of periods of year is going to go to infinity, and that should ring some kind of distant calculus bell. You take the limit and, et cetera, et cetera. So if we do take the limits here, what we find is that the formula relating our future value to present value with continuous compounding works like this. The future value is equal to the present value times e raised to the APR. So here's another use, arguably, for APR times t, where t is always going to be in years for us now. Okay, and also another formula here, the equivalent annual interest rate for a deal with continuous compounding is e to the APR minus 1. And e is, of course, our universal exponential constant, 2.718, et cetera, et cetera. 2.718, plenty good enough for significant figures for our purposes. Okay. So let's do a couple of quick examples here. So what is the value of a $100 investment after 2 years given 6% APR compounded continuously? Okay, so we'll just use the formula on the previous page or the grayed out material for those of you who might be able to see that. Future value for the continuously compounding world is equal to present value times e raised to the APR times t, okay, and that's equal to what in our case, 100 times 2.718 raised to the, of course, raised to the, our APR is 6%, 0.06 times 2, okay? And if you work that out, you get 112.75, okay? All right, so what is the EAIR of this investment? We're just going to plug in the formula on the previous page. It's equal to e to the APR minus 1, which is 2.718, raised to the 0.06 minus 1, and that's equal to 6.18%. Okay. All right. So that's where we are with that one. That's pretty much all we need to know about continuous compounding. If you're going to become a financial engineer, in other words, if it's your goal to help create the next greatest recession since the Great Depression, you will need to know more about this to use calculus and various financial machinations that may cause the economy to crash if applied at large scale. Okay, so the next thing we need to spend a little bit of time on as a review is inflation and real and nominal interest rates. Okay, so let's start with inflation, and hopefully this is a little bit of review. Inflation is defined to be the rate at which overall prices are rising. It's usually reported in percent. There are a couple of common measures of inflation in the U.S., the GDP deflator and the consumer price index, and we're going to stick with, for our purposes, the CPI, which is measured by the federal government, and the CPI is just the cost of a specific basket of goods or services that are all purchased in the U.S. Okay, so every year, a branch of the U.S. government goes out and sees what this basket of goods and services would cost. So in 1998, 163, all the way up to 2007, 207. And of course, they adjust the basket of goods and services a little bit to account for things like changes in technology. No such thing as a cell phone in 1970. Now they're very common, etc. So it's a little bit of a sticky wicket, a little bit tricky, because how do you appropriately change the basket is a non-trivial question, etc., etc. Okay. But that's neither here nor there for right now. Let's just assume they do a good job at this and they have the right basket every year for right now. So here is a graph of the CPI coming from 1900 all the way to 2010. And so you can see that prices don't always go up. Sometimes they go down, specifically in the Depression, they went down a lot, but even before that, prices went down a lot occasionally. And you can see things have gotten much more stable since the 80s and remained pretty stable. Inflation has been quiescent for the past 3-4 years, sitting here now in 2017. Okay, so also, once we've got the price of this basket of goods in 2 successive years, we can compute the rate of increase. So we can say here between 1998 and 1999, end of year, so that would mean from beginning of 1999 to end of 1999, the annual inflation rate was 2.2%. That means overall prices in the economy were increasing by 2.2%. So from the beginning of 2003 to the end of 2003, the price of the basket of goods goes from 180 to 184, an increase of about 2.3%. All right. So we see on this page how to mathematically compute those numbers to get the rate. We just get the CPI at the end of the period minus the CPI at the beginning of the period, quantity over CPI at the beginning of the period. We could once again apply a little bit of the magic of algebra there to simplify that. Not necessary, but interesting to note. So for the year 2007, at the end of the year, the basket cost 207, beginning of year 202. So we take 207 minus 202 over 202, and we get 2.8%, and that better be the number that we have here for 2007. Yes, it is 2.8%. So that's looking good. Okay, we can also go for more than 1 year at a time. There's no law that says that we have to compute inflation rates only annually. The inflation police won't come around and arrest us if we look at the rate of inflation from, say, end of year 2000 to end of year 2007. So we could compute that. We have using the refined formula here, we have inflation at end of 2007, the CPI at end of 2007, 207.34, and end of year 2000, the basket cost was 172.2. So we do that division, subtract 1, and we get 20%. So what do we mean by that? What does that 20% mean? Well, we've got it right down here. That means that inflation increased prices by 20% from the end of year 2000 to the end of year 2007. Okay, so we could also look at CPI increases the way engineers like to look at this, using the price increase factor. And you can see here the price increase factor for inflation over a period of time is just the ratio of the CPI at the end of the period divided by CPI at the beginning of the period. So for that period, 2000 to 2007, again, the price inflation factor is just 207 divided by 172, or 1.2. And we'd say goods were 1.2 times more expensive at end of year 2007 than they were at end of year 2000. Okay, so one reason that we look at inflation is to help us intuit what's going on with real and nominal interest rates. So a good way to suss this out is just to jump right in with an example. So let's say at end of year 2007, Blah Bank offers a 1-year 2% CD, okay? And we know that inflation is running at 2.8% at this time. So that would be, what I mean by that, that would be one of these numbers, okay, 2.8%. So we could say that maybe that's at the end of 2001, we'd say that inflation is running at 2.8%, okay. Blah Bank says that if you invest 100 in our CD today, okay, because we're giving you 2%, at the end of the day, you're going to be able to buy less a year from now than you could buy now, assuming the inflation rate stays constant at 2%. So I would say whoever is in charge of marketing at Blah Bank should be fired, because they probably don't want to pitch their horrible product in that way. But that is the truth, the whole truth, and nothing but the truth, right? So if we put 100, what do I mean by that? If we put 100 in Blah Bank's investment today, we'll get $102 in a year, but the cost of goods and services in the economy has increased by 2.8%, so we'd really need to get back $102.80 just to keep up with inflation. But Blah Bank is offering a crummier deal than that. It doesn't keep up with inflation, so what we would say is that investment will be worth less in real terms a year from now, or what we would say is the real return on this investment is negative. Okay. All right. So with that in our pocket, let's define a couple terms here and see how we can put everything together. Inflation, real rates, nominal rates. All right. So the nominal interest rate, R, is what we have been using so far. Okay, and it's the rate at which our investment capital grows. Okay, so even though it's called nominal, it's what we've been using so far, and it is very commonly used. All right. The real interest rate, which we'll start calling R sub R, is the rate at which the purchasing power of an investment grows, okay? And this is something that economists use more than most other people, used in finance. But if we're looking at specific projects, like we have been, like we're going to continue to, we're going to be focused on the nominal interest rate. All right, so can we switch from one to the other? We're always interested in that. And yes, we can. Here's a sort of complicated equation for doing that, 15J. If the inflation rate is relatively low, let's say something like this, let's say less than 5%, we can use this simplified formula where we say the real interest rate is sort of kind of equal to the nominal interest rate minus the inflation rate, which is sort of intuitively obvious, as we'll see in a second. Okay, so for our blah bank example, okay, we had a nominal interest rate. They said that contractually your money is going to grow by 2%. That's the nominal interest rate. I know it's weird to call it nominal interest rate, but it is. Just get used to it, please. And inflation, we said, is running at 2.8%. So what is the real interest rate on this investment? Or we could also say the real return on this investment. And if we plug in the fancy formula, 15J, okay, we're going to get, we know the inflation rate, 2.8%, we know R is 2%, we can do this math, right, and work it out. We work everything out. We solve for RR, the real rate, and we get minus 0.78. Using the simplified version, is the real rate is our nominal rate minus the inflation rate. We get something pretty close. We get minus 0.8%, okay? So good enough to use the simple formula, which I think is fairly intuitively obvious. And what would we say after doing this analysis? We would say that the purchasing power of an investment in blah bank CD would decline by 0.8% a year, okay? Or we could say, if we wanted to, equally good, the real return of blah bank CD is minus 0.8% per year, okay? So that's how we use this. Couple notes on this. Any time value problem can be done with either nominal rates or real rates, but the cash flows have got to match our rates, okay? So if we're working with real rates, we've got to use real, i.e. inflation-adjusted cash flows. When we work with our nominal rate, we want to use nominal or normal cash flows, which we have been doing all the time, okay? All right, this is important because if we wanted to switch to real rates, all of a sudden we would have to adjust every stinking future cash flow in every problem we've done to date to put it in real terms, okay? So in the real world, almost everybody who's doing a time value problem is going to be assuming nominal, i.e. normal interest rates, discount rates, and cash flows, okay? And that's going to be moving forward our assumption unless otherwise noted. Okay, so let's do an example here. It's a pretty good example, if I do say so myself, that helps us put everything together and see how this all works out. So given gas prices at the end of the year 2000 were about $2 a gallon, average national price. By 2007, the price was about $3.50 a gallon. And we can look back and see that the CPI at end of year 2007 was 207.34, and the CPI at end of year 2000 was 172.2. So with this knowledge, we can answer questions like this. Did the gas price decline or increase in real terms over this period? There are several ways to solve this problem. Let me show you how I solved it. If you want to solve it a different way, that's fine, as long as you come to the right conclusion, okay? So here's how I did this. I said that overall prices increased by this ratio of 207 over 172, or 1.2 times, or 20% in this period. So then I just said, okay, well, if gas prices rose with inflation, I should be able to take the 2000 price and multiply it by 1.2 and get the 2007 price. So I take 1.2 times 2. In most circles, that's 2.4. So if gasoline rose with inflation, the price at end of year 2007 would have been $2.40 a gallon. We know it ended up at $3.50 a gallon, so clearly that's not true. Gas was not rising with inflation. It was rising faster. If it's rising faster, what does that mean in real terms? The gas price increased in real terms. Okay, so that's how I solved this. Like I said, many different ways to skin this cat. So now let's ask the question, how much of the gas price increase between 2000 and 2007 is attributable to overall inflation, and how much is attributable to what economists would call exogenous factors? Okay, so the general inflation increase led us from 2 to 2.4. So we subtract 2 from 2.4, and we say that 40 cents worth of the total increase was due to general inflation. Okay, but remember, it went up all the way to 350. So to get the rest, we take 350 minus 240. That's $1.10. That was due to other causes, which was specifically oil price shock from Gulf War, etc. Okay. All right. So this inflation measured by CPI stuff, and the concept of real versus nominal returns can help us solve some interesting problems like this one. Okay, and I think that's it for now, and very soon we will pick up with the next chapter. So out for now.